billahi minash shaitanir rajim. Bismillahir Rahmanir Rahim. Dear students, today we are discussing Lebesgue integral. Now we have a definition. Let us suppose that function fx, which is bounded and measurable on ab closed interval. Since fx is given to be bounded, so by definition we can find a real number alpha and beta such that fx is greater than alpha and less than beta. As function is bounded, it means that all the values of the function must be in between alpha and beta. Or we can also say that fx greater or equal to alpha and less than or equal to beta for all the x belong to AB closed interval. There is only equality. Fx can be equal to alpha and fx can be equal to beta, and all the values of x can be in between. Now let us divide the range alpha beta into n parts using the partitioning points. Range means y-axis, and the partitioning point of the y-axis starting from alpha is equal to y naught less than y1 less than y2 less than dash 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 less than yk minus 1 less than yk less than dash 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 less than yn minus 1 less than yn equal to beta. These partitioning point has been shown on y-axis. Now on y-axis we have different points y naught, y1, y2, y3, dash dash dash, yn minus 1, yn, and domain is our AB closed interval x-axis. Now we see that between y naught and y1 point there are the function values, and on domain the function value is e1. Similarly between y1 and y2 points we get the function fx, and on domain fx represented by e2, and similarly y2 y3 there is a function fx, and on domain this function is e3, and dash 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 for the point yn minus 1 and yn there is also a function, and we get the in domain that is en. So the set y is equal to alpha is equal to y naught comma y1 y2 dash 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 yn equal to beta is called a mode of the partition or subdivision, which can be varied. It means that we can take different points, that is y naught y1 y2 dash 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 yn. Now let us define a set ek as ek is equal to x belong to AB closed interval such that fx is greater or equal to yk minus 1 and less than yk. This is the general representation of ek. If we put k is equal to 1, e1 is equal to x belong to AB closed interval such that fx is greater than or equal to y naught and less than y1. Similarly e2 x belong to AB closed interval such that fx is greater or equal to y1 less than y2. e3 x belong to AB closed interval such that fx is greater or equal to y2 and less than y3, and dash 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 en x belong to AB closed interval such that fx is greater or equal to yn minus 1 and less than yn. Now since function fx is given to be measurable on AB closed interval, so according to the definition of the measurability of the function, the set e1 e2 e3 dash 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 en are all measurable and are all disjoint. Function is measurable, then e1 e2 e3 dash 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 en are also measurable. So we define the upper sum capital S and the lower sum small s as under. As capital S is equal to summation k is equal to 1 up to n yk m of ek. Yk represent the length of the interval and mek represent the width of the interval. So the upper sum is the product of yk m of ek summation k is equal to 1 up to n, and similarly small s is equal to summation k is equal to 1 up to n y of k minus 1 m of ek, that is the lower sum. So in the lower sum instead of yk there is yk minus 1. Yk minus 1 represent the length of the interval or height of the interval, and mek is the width of the interval. So the lower sum will become small s is equal to summation k is equal to 1 up to n yk minus 1 m of ek. By varying the mode of the partition, we get a set of the values of the capital S and small s. It means that we can change the mode of the partition. We will get different capital S and different small s. We take capital J, that is the GLB of the capital S upper sum, and I is equal to LUB of the lower sum. I represent GLB of the upper sum, J represent the GLB of the upper sum, and I represent the LUB of the lower sum. The values of J and I will obviously exist because the function is given to be bounded, and there is a must value of capital J and there is must value of the capital I. So also we write I is equal to integration a to b fx dx. I represent the LUB of the lower sum, and J is equal to integration a to b fx dx. As a function fx is called Lebesgue integrable if I is equal to j. If we got the value of I is equal to j, then the function is Lebesgue integrable, and then its common value is given by I is equal to j is equal to integration a to b fx dfx. It means that function is Lebesgue integrable.